All right. So let's get started. Good morning, afternoon, evening, everybody, and welcome to tutorial MH7 on recent advances in integrating machine learning and combinatorial optimization. I'm Elias. I'm an assistant professor at the University of Toronto, and I'm happy to be co-presenting this tutorial with colleagues from Polytechnique, Montreal, and the Canada Excellence Research Chair in real-time decision making, and the University of Southern California, USC. Just a couple instructions for questions. Please type them in the chat, in the Zoom chat. We will keep an eye on that. The co-presenters will try to answer your questions live in the chat. And if any questions remain, then the presenter of that respective part will try to answer your questions right after they present. And because we have a kind of a packed schedule, we might not be able to answer all questions right after the presentations. We have a couple of breaks here and there, so you could try to also get answers to your questions in the breaks, or maybe a bit after the whole tutorial for those presenters of us that are able to stay. Okay. So our tutorial is in 7 parts, and I'll start with the first 2, introducing kind of the overall setting of combinatorial optimization and kind of an overview of the tutorial. And then I'll talk about one aspect of learning and combinatorial optimization. So the setting we're in is the following. As humans or computer scientists, we learn to design algorithms as part of our training. And for many of us, this is kind of a routine activity, and we do a lot of it, regardless of whether you're in AI or other areas of computer science or engineering. And so one key question we will deal with in this tutorial is the following. Can algorithms learn to design other algorithms? So the first kind of algorithm we're thinking about is machine learning algorithms. And the second type of algorithms we're thinking of learning to design is combinatorial optimization or discrete optimization algorithms. And so when I say combinatorial optimization, what do I mean? Let's take this example of data center resource management. So a company receives a bunch of requests for services. Each of the requests comes with some amount of CPU that's requested and some amount of memory. If you're in a university, this is extremely common when you use any kind of shared computing cluster. We have a bunch of machines which have different CPU, memory resources. And we would like to assign these jobs or services or requests to these machines in a way that optimizes some objective. So one natural objective is we would like to use the smallest number of machines to be able, while servicing all these requests. So that's one potential objective function. So in this tutorial, one paradigm that we will use to mathematically model or formulate such problems is the mixed integer linear programming formalism. And it looks something like this. So within this data center resource management problem, we're going to define 2 types of decision variables that happen to be binary. So ym is set to 1 if a machine m is used, okay? And a variable xsm is equal to 1 if a given service s runs on a given machine m. So these are both binary variables. There are as many x variables as there are services times machines, and as many y's as there are machines. And let's say we'd like to minimize, again, the number of machines being used. Okay. Now, obviously, you could not use any machine, but not service any jobs. So we need some constraints to express the fact that jobs need to be assigned to machines. So these constraints in many scenarios can be expressed as linear equalities or linear inequalities. And here we're talking about them being linear in the decision variables. So for example, one constraint is that each service should run on one machine only, should not split it over multiple machines. A machine is on if some job is assigned to it. so that, you know, this ym needs to be greater than or equal to all xsm. So if any xsm for a given m is set to 1, then the corresponding y is flipped on, and then you pay for it in the objective function. The machines have memory capacities, so we should make sure that whatever jobs are assigned to that machine don't exceed that capacity. And so in green, we have mem_s, which is the requested memory for a job s. And the same can be said about processor capacity. And of course, this is a simplification of many real scenarios, but it actually captures a lot of the, you know, considerations for this type of resource management problem. So this is one kind of combinatorial problem, and this is how we think about it in terms of integer programming. Another problem that arises in machine learning, and which has received lots of interest recently, is in safety critical machine learning. There, you've already trained some kind of neural network, say to classify stops or traffic signs in the simple case as, you know, is this traffic sign a stop sign or a yield sign, right? And so maybe you want to use this in some autonomous driving setting or the like. And so you've trained such a model, and people have observed, you know, starting 5-10 years ago, that these models can be prone to adversarial perturbations. So you add some small amount of really, you know, intelligently constructed noise. So this kind of gray matrix, which really seems like nothing. And then all of a sudden this neural net, instead of, you know, outputting stop, you see it's now outputting yield. And this obviously can be dangerous in practice if you're using this in any kind of real-time autonomous driving system. And so one thing you might like to have for this model is to guarantee that the trained model has some desirable behavior. Let's say you want it to be robust to a certain type of perturbation. So given a pre-trained model, you would like to make sure it's not gonna make such mistakes. And it's been shown that you can model, for example, the ReLU activation function, the rectified linear unit, which you see here in these black nodes of the neural network. You can model it with binary variables and linear inequalities in a way that's very similar to what I showed you in the data center resource management example. Once you model this neural network as a function with these binary variables and linear inequalities, then you can solve a verification problem, which says, prove that there does not exist, you know, a perturbed point x prime, which is close to x, such that the model f, we call it f just because it represents some function, we don't want this model to predict yield. So we want the output f for, you know, perturbation x prime to be bigger for stop than it is for yield. So prove that there does not exist such a perturbation. And you can frame this in the same mixed integer linear programming language and try to prove that this is true or not. And third, a more classical type of operational problem, which is kind of where most of mixed integer programming was developed, is in forest harvesting. And so there, you would like to design a strategy to harvest certain parts of a forest, subject to constraints on, you know, not kind of destroying connected parts of the forest. And so let's say you take a certain parcel of land, you superimpose a grid on top of that. From that, you get some kind of graph where each node is a cell in this grid, and two nodes are connected if you know, they are physically accessible from one another. So you get this kind of undirected graph. And then you can ask, I would like to harvest a subset of parcels. So this is a subset of these nodes to maximize revenue. So let's say, you know, you can estimate some revenue that's associated with something like the area or the kind of wood that you can harvest. And you can pay a certain cost for harvesting adjacent parcels. So for environmental reasons, you know, you don't want to harvest too many adjacent parcels. And so if you do that, you pay some cost. So to formalize this, you can also write down a similar, you know, mixed, in this case, integer linear programming formulation, where the objective function is to maximize this difference between revenue and cost, subject to a certain constraint on on adjacent, on harvesting adjacent nodes. And this is a generalization of the famous independent set problem. And so these were just 3 examples of the kinds of problems that the combinatorial optimization framework encompasses. And there are many, many more. And so here I list only a few of them. A famous one is in political districting. Also, lots of kidney exchanges are optimized with integer programming. These days, ride-sharing apps also require some kind of matching and assignment subject to constraint, which can be addressed with integer programming. And more classical applications also include airline scheduling, for example. And it's been estimated that, you know, if you want to estimate kind of the financial value of this kind of combinatorial optimization framework, if you can look at certain awards from this prestigious Informs Edelman Award, which targets kind of very high impact applications of analytics and operations research. And George Nemhauser a few years ago counted that more than half of the winners of that award were using some kind of discrete or combinatorial optimization in their solutions, which would translate to, you know, hundreds of millions or billions in savings or profit. So this is really a very high impact framework. And so we would like to naturally think about ways to improve solution methodologies. Okay, so going back to the data center resource management problem, I gave an example of one instance of this problem. In practice, what would happen is you would typically solve, you know, this resource management problem multiple times. And so you might do the assignment at 4 p.m., another time at 5 p.m. when you get another set of services or jobs you need to service, and another time at 6 p.m. and so on and so forth. And clearly the frequency here of 1 hour is just for the sake of illustration. The frequency could be, you know, much higher or much lower depending on the application. And you notice, if you look at these 3 different instances of the same problem, you know, the jobs are different. So they require different CPU, different memory, and then the machines available could also be different. Some machines could be down, etc. This is to say that kind of the underlying data of the problem is potentially changing, but kind of the problem is the same. So all these problems are relatively similar. They have the same underlying mathematical formulation, and the data is changing a bit. Okay, so how do we tackle these integer programming combinatorial optimization problems? From the computer science perspective and also operations research perspective, there's really 3 ways you can think about in tackling these NP-hard optimization problems. The first one is exhaustive search. And there you try to design, you know, nice mathematical formulations, what we call tight formulations, and potentially leverage existing branch and bound solvers, which are essentially 3 search algorithms for integer programming problems. And we'll talk a lot more about this kind of approach. So this is one way to tackle these problems. Now, if it turns out that the exhaustive search takes a lot of time because it's kind of exponential time in the worst case, computer scientists like to look at approximation algorithms. And there, the design rationale is to derive a good worst case guarantee that says, you know, this algorithm is going to return a solution that's within this factor of optimal for any input. So this is another approach. But, you know, sometimes deriving these guarantees can be very tricky. And so what we end up settling for in practice is, you know, heuristics, which may not have the guarantees of either exhaustive or approximation algorithms, but kind of, you know, we use some intuition about problem structure to derive like effective heuristics, and we try to evaluate those on some instances of interest and maybe tweak the heuristic here and there to try to you know, get it to perform better. So these are 3 common frameworks or paradigms that you can use to tackle NP-hard optimization problems. Now, let's think about what happens when you have multiple instances of the same problem. Like in this data center resource management problem, you have multiple instances from different times of day. How would you improve these paradigms in order to kind of perform better given this knowledge or this data that you're able to accumulate? Okay, so how do you tailor the algorithm to your instances, not to the worst case instances in theory? So in exhaustive search, what you can do is you can tailor this tree search or branch and bound by deriving certain problem-specific bounding functions or search rules. So you try to guide the search in a way that leverages some mathematical structure potentially in the optimization problem. So this is one very common way in operations research. This is something that's very commonly done. In approximation algorithms, instead of thinking about worst case guarantee for any instance of, say, this data center resource management problem, this assignment type problem, you make explicit assumptions about the distribution of the input. So maybe you assume that the CPU requirements of jobs come from some Gaussian distribution, which has certain bounded variance, for example. And then you redesign your approximation algorithm to exploit that knowledge and maybe derive better guarantees than the worst case approximation guarantees. So that's how you would do it for approximations. As for heuristics, what you do if you have a set of instances, you would just run this algorithm and kind of manually tune its own parameters and try to look for patterns that you can exploit so that this heuristic performs better. So the key takeaway here is that all of these three customization approaches require significant manual kind of labor, either intellectually, meaning you have to think about the theory of the guarantees of your approximation algorithms, et cetera, or derive better bounding rules for your tree search, or experimental effort, as in the case of heuristics. And often you might need a combination of the two. So your theoretical intuition might not match the practice, and you have to go back to the drawing board after running some experiments. And so it takes quite a bit of work. And so one thing we will focus on in this tutorial is this idea of automatically tailoring algorithms to a family of instances. And we will try to showcase different ways of achieving that, primarily within the mixed integer programming framework, but also within kind of the graph optimization or combinatorial optimization framework, which doesn't use necessarily integer programming formalisms. And so we will illustrate how one can develop machine learning approaches that improve these algorithms based on data automatically. And I mentioned some applications of this kind of approach, but there are many, many more, and my co-presenters will touch on some of them. So this is one key aspect of this tutorial, which we will focus on in parts 2 to 5 today. So another aspect of this tutorial deals with how the optimization problems themselves are formulated. So going back to the data center resource management problem, I've highlighted in yellow this memory requirement and CPU requirements of a given job S. And so what I was assuming when I presented this problem to you was that this information was given to me, right? So it could be that if you think about scheduling jobs on a cluster, the user comes in and says, I need 10 hours and 8 gigabytes of RAM. So this is a reasonable starting point. But we know from our personal experiences as researchers that we will tend to typically overestimate how many resources we actually need. So if I know I need 4 gigabytes, I might ask for 16 because I fear that somehow I have a bug and my job will crash sooner. Or I know the job takes 2 hours, but I'm hedging against some weird scenario in which it takes longer. So I ask for 12 hours instead of 2 hours. And so if you're managing the cluster and scheduling jobs, ideally what you would want is maybe have your own more accurate prediction of these parameters of the optimization problem, namely the memory and CPU requirements. And this is actually done in this very specific setting. And so where does this information come from? One way to do that is you can train some kind of machine learning model on historical data. And so instead of using the user provided CPU requirement for a job or a service S, you have some model, supervised learning model, regression model, that has parameters theta. And you compute some features of the service or job S, you run it through your model, and then you obtain your own prediction for the CPU requirement. And then you put that into your integer programming formulation, run that through some optimization solver and obtain, an assignment. Okay, and so this particular interaction between machine learning and combinatorial optimization, namely what happens with predictions of parameters of optimization problems and how can we train models, machine learning models that are accurate for the optimization task, the downstream optimization task, is another key aspect of this tutorial. What has been, has become known as decision focused learning, and this will be part 6 of the tutorial. And so the goal will be, how do you train machine learning models that accurately predict parameters of optimization problems, and there Bistra will illustrate various applications and methods that can achieve that. Okay, so this brings us to the end of part 1. I assume there are no questions up to this point.
No, so there are no questions from the chat.
Okay, cool. Yeah. So I will continue with the second part of the tutorial, and then we'll take a 15-minute break after that. Okay, so to get into the kind of the crux of the tutorial, I will start by looking at a pure machine learning approach that kind of predicts feasible solutions to optimization problems. Before that, one might wonder, why not just use existing hyperparameter tuning approaches, which have been, very widely successful in, say, machine learning, to tune optimization algorithms or optimization heuristics. So to illustrate this, what you're looking at here is a screenshot of the documentation for Cplex, which is a very widely used commercial solver for integer programming. It has a very wide range of parameters. In machine learning, you would call that hyperparameters, but here we'll just call them parameters. And zooming in to 2 such parameters, the first one, which deals with the variable selection strategy or the branching strategy. The second one at the bottom deals with the heuristic frequency. How many, how frequently should the solver try to execute some heuristics during an exact tree search? And you can see that the first parameter here, the variable selection strategy, has 5 predefined or 6 predefined values. And there's one of them which is default, in which the solver picks its own strategy without telling the user what it's doing necessarily. And the others, if you're kind of an expert user, you can try playing around with the other values and choosing other strategies. As for the heuristic frequency at the bottom, it's kind of an open integer, just any positive integer will do, or you just input 0, you let the solver decide itself what this frequency should be based on its own internal criteria, which we don't really know. Okay, so there's lots of parameters like these. And there's kind of a very solid methodology, which is called algorithm configuration, which says we can search in the space of such parameter configurations. Okay, and so you're given, this configurator is given domains for the parameters, and then it calls the solver with different configurations, and it tries to kind of find good regions in the parameter space that maybe solve your set of training instances in a short amount of time. So you would define some performance metric and to try to optimize for that. Okay, and I cite here one such paper which talks specifically about configuration of mixed integer programming solvers. And the idea is that this search is carried out using some kind of iterative or stochastic local search or Bayesian optimization, basically a kind of black box optimization. You assume that the solver itself is close to you. You can only query it with certain parameter configurations and see how it performs, but you don't really know much more about its performance. And it's been shown to work really well. For example, for Cplex, maybe 10 years ago, it's been shown to provide a speed up of 2 to 52x in runtime on various problem distributions. However, it suffers from a very important limitation that I have highlighted here at the bottom. These kinds of algorithm configuration or parameter configuration approaches operate at the instance level, meaning they do not modify the iteration level behavior of the algorithm. And so when you change a parameter setting, that's it. That's the granularity of the change that you can make. And that might be very useful in some cases. But if the parameter space is not rich enough and there does not exist a good parameter configuration for the set of problems you care about, then it's unlikely that this approach would help you very much, because it's not able to control the solving at a granular enough or fine-grained enough level. And so to kind of move you more towards the type of learning within algorithms that we're interested in, I like this example from Khalil, who looked a few years ago at learning within gradient descent. So this is not the combinatorial setting. This is the continuous optimization setting, which may be familiar to most of you here. And so Khalil's illustration here compares, at the top, say a standard gradient descent, at the bottom, a learned optimizer or a learned gradient descent. And so at the top, you see that gradient descent is somehow oscillating around the optimal solution. And so it's unable to converge very fast, keeps going back and forth. Whereas the learned optimizer, because it's seen some historical instances, similar convex functions, let's say, it's able to realize, I've seen this situation before. I've been in a similar kind of neighborhood or landscape before. So let me adjust kind of my learning rate or the direction with which I'm moving in this gradient descent algorithm to converge to an optimal solution faster. And if you were to write this down in pseudocode, basically, instead of looking at this delta x, what we typically compute as just the gradient update, so this thing in yellow here with gradient descent, you might have a learned algorithm which looks at the current iterate, it looks at maybe the sequence of past iterates, the function value, etc., and it might pick another direction than the one suggested by just the gradient. Okay, so you see here that the level of control over the algorithm is very fine-grained. It's at the iteration level, and we will be generally looking at a lot of these kinds of approaches, but also at higher level decisions, but in a more kind of white box way, as opposed to the black box approach of parameter configuration. So moving towards combinatorial optimization, we'll consider the example of the vertex cover problem, minimum vertex cover problem, where you're given an undirected, in this case, unweighted graph, and you would like to pick a subset of vertices such that each edge is covered, meaning each edge has at least one of its endpoints in the cover that you've selected. So this is a canonical NP-hard optimization problem. And we know that there exists a two-approximation algorithm for it, which greedily adds the vertices of the edge with the maximum sum of degrees of the nodes. Okay, so for example, in this figure that you're seeing, this edge connects two nodes which happen to have very high degree. Okay, and actually you don't even need to add the highest degree, but this is one kind of particularly effective variant in practice. So we know that this greedy heuristic will give you a two approximation, meaning by the time this algorithm terminates and all the edges have been covered, the size of the set of vertices is at most 2 times the minimum possible. However, one can imagine that this two approximation is kind of a worst case guarantee. If you have a specific set of graphs coming, say, from a social network type application, like I'm trying to insinuate here, then potentially there are other greedy node selection rules that might lead to better solutions on average, just empirically. So you might not be able to prove nice two approximation guarantees for them, but just prove empirically that they work well on the kinds of instances that you care about. And so we started looking at this a few years ago in this NeurIPS 2017 paper. And so here I'm gonna present this general methodology for improving graph optimization problems with machine learning, specifically deep reinforcement learning. But this approach has been kind of extended in many directions since. So take this as just one example of how you can achieve this. And I will touch on a bunch of follow-ups that improved this overall methodology or extended it to other problems. So the kind of problem we're looking at, to state it a bit more formally, is the following. We're given a graph optimization problem G, say the minimum vertex cover problem, a distribution D of problem instances. So think of it as, in the typical supervised machine learning setting, you assume that you have a distribution over data points, X and Y, and all your X and Ys are drawn from the same distribution. So we're given this graph optimization problem G, a distribution D of problem instances from which we can draw a set of training instances. And the question is, can we learn better greedy heuristics that generalize to unseen instances coming from the same distribution, right? So this is kind of a formalization of this problem in the typical machine learning language, okay? And this kind of problem statement doesn't apply only to vertex cover. In fact, there are lots of graph optimization problems where a kind of greedy strategy, which sequentially selects nodes, is a very reasonable strategy. And greedy algorithms, are very common heuristics for many optimization problems. And so not only can you apply this kind of idea to vertex cover, you can also look at the max cut problem, where you're looking to partition a graph into two disjoint sets, such as the sum of the weights of the edges crossing between the two sets of the partition, the sum of the weights is maximized. Also, you can apply the same kind of thinking to the traveling salesman problem, where you're given a bunch of cities, say on a grid, and you can think of them as being connected by the complete graph, where the edge weights correspond to the cost or the distance between two cities. And you would like to construct a greedy strategy that selects nodes in sequence and completes a tour. And hopefully that greedy strategy gives you small or short tours on average on your distribution of instances that you care about. And so we're given a graph problem and a family of graphs, meaning training graphs sampled from that distribution. And we would like to learn a scoring function that guides a greedy algorithm every step of the way. So a first useful mapping or reduction that you can do is from greedy algorithms to reinforcement learning. So in a greedy algorithm, you deal with the notion of a partial solution. So these nodes in the graph that you see in the blue squares, this is our current partial solution, let's say. In reinforcement learning, you would treat that as a state, okay? The greedy algorithm uses some scoring function. You see these green bars next to the nodes, which assign some score expressing how desirable it is to add a node. And this is very similar to the Q function in reinforcement learning, kind of the value function. What is the value of adding a node to my solution in terms of the final objective function. Last, in a greedy algorithm, you always select the best node according to these green bars, to the scoring function. And in reinforcement learning, one optimal policy is the greedy policy, where you use the Q function and do an argmax over the Q values for the current actions. And so you have this very natural mapping between how a greedy algorithm behaves and how we describe reinforcement, the reinforcement learning framework. And so in that light, you can view this greedy algorithm as doing the pseudocode in the box. Until all edges are covered, we iteratively, at every iteration, compute the node scores, select the best node with respect to the score, and then add the best node to the partial solution. Then the reinforcement learning question becomes learning a scoring function, this thing in green, so that we select strategically based on that and get good solutions which have small, say, vertex cover cost, meaning the size of the vertices that cover all edges is small. Okay. So to do so, we need to represent nodes somehow. And so specifying a bit more what this Q function looked like, this is known as the action value function. So this function Q hat takes the current state, which we said is the partial solution, and a given vertex, which we care about, which is not in the partial solution. The Q function has some parameters theta. These are the typical kind of parameters you're learning in reinforcement learning. And the role of this function is to estimate the goodness of a vertex V in a state ST. Now, how do you represent V so that you can pass it on to this Q function? First approach is you have some kind of feature vector that describes a vertex V in a state ST. And you can do that with some kind of feature engineering. You look at the degree of the node. You look at, you know, the two-hop neighborhood size or two-hop degree. You compute the page rank or between the centrality, etc. So you can use all kinds of graph centrality measures or the like. And you get some feature vector for V, and you try to learn with that. The issue with this approach is that if you go from vertex cover to max cut, from max cut to traveling salesman, it's not clear that the same features are useful across problems. And so you need some amount of task-specific engineering. Second, it's hard to know in advance what a good feature is. So for example, for vertex cover, we know that the degree is good because somehow there's good approximation algorithms that leverage the degree. But it's unclear that if you have a specific kind of graph structure in your data distribution, that the degree is very indicative. It could be that, you know, the graph is kind of regular, most nodes have similar degrees, but there's some other structure, some kind of clustering structure or the like. Third, it's difficult to generalize across different graph sizes because computing these features will require some kind of normalization, etc. So they will depend naturally on the size of the graph. So it's unclear whether if you go from, you train some reinforcement learning agent to solve this problem on, you know, small graphs, would those features still be useful on larger graphs? And so there's a few problems with doing feature engineering if you want a kind of a generic reinforcement learning method for these graph optimization problems. And so instead, what we do is we try to leverage the very useful paradigm of graph neural networks or graph embeddings, where we parameterize some graph neural network with these parameters theta. And what that graph neural network is going to do is going to learn to represent a vector for each node such that the vector maps to good scores or good estimates of the goodness of the node. So these green bars. And I won't go into details of how graph neural networks work, but the key idea is essentially to do representation learning rather than to fix or engineer, pre-engineer a feature representation for your graph. And so this way, we don't need to do feature engineering. The features are parameterized and trained to be good via reinforcement learning. And you can also naturally handle different graph size because the way these graph neural networks model are designed is such that they are invariant to graph size. So they don't think of, they don't need to assume that you have a fixed size input. And so if you train a graph neural network model on graphs of size 100, you can apply the same model directly on a larger graph because the parameters of the model theta are kind of local or shared. They don't depend on the size of the graph. And so this addresses you know, all the issues that you would have with feature engineering. And so combining the reinforcement learning view with this representation learning view, you're able to then leverage standard algorithms for reinforcement learning. So in the case of this particular paper, we used the Q-learning algorithm, and other papers I will briefly touch on next used other algorithms like policy gradient. And the main idea is if you look on the right-hand side here, this reinforcement learning algorithms is trained as follows. You sample a graph instance from your training distribution. So you might have a synthetic generator or just a fixed set of training graphs. You either explore or exploit based on your current policy, which is defined by this function Q. Then you update your state, meaning you add this newly selected node to your partial solution. And then you do some parameter update so that these theta parameters that determine the scoring function or the Q function are made to be closer to what the true observed reward is. So this is the standard kind of, you know, regression update that you do in reinforcement learning. And so combining these two, you can learn a greedy scoring function that will give you a good cumulative reward. In this case, for vertex cover, for example, a small vertex cover. And so the framework can be summarized as this. You take a graph, you embed it with a graph neural network, which is illustrated inside this box. It suggests some scores, these green bars, and you add the best node based on that. Then you take this new graph with the current partial solution and you embed that again. And you keep doing that until you've covered all the edges. Okay. And so we've applied this framework, as I mentioned earlier, to various problems, including vertex cover, maximum cut, and the traveling salesman problem. And what you're seeing here on the vertical axis is the approximation ratio. So 1 is optimal, and otherwise it's a distance to optimal, and it's an average over thousands of testing graphs. And our method is always shown on the leftmost set of bars, and the different sets of bars refer to different sizes of the graphs. And so we've compared to other machine learning based approaches, but also to standard classical heuristics that involve no learning. And we were able to showcase how this approach is able to get very good approximation ratios, even compared to very well-known classical heuristic. And the code is available and has been extended quite a bit for various other graph optimization problems. And so in this case, we use some data-driven algorithm design. This is kind of what we call this approach, and it's able to automatically discover novel search strategies. So what you're seeing in the illustration is a comparison of a vertex cover solving process between a learned heuristic on the left and a classical heuristic on the right. Whenever they cover an edge by picking the next, the new node, this edge disappears from the graph. And so the method that gets to an empty graph has solved the problem with a smaller vertex cover. And you can see that the one on the left, the learned heuristic, is going to solve faster than the classical heuristic, this greedy approximation algorithm. And it does so in a very interesting way. You will notice that the method on the left tries to maintain one big connected component, whereas the method on the right is going to break up the graph. So notice how classical heuristic is going to start to have all these disconnected components, whereas the learned heuristic kind of maintains one big block, and that allows it eventually to find a smaller vertex cover, although we have not really infused this knowledge during the training. So this was kind of behavior that emerged, at least qualitatively, from the reinforcement learning process. And so we're able to discover some nice novel search strategy, which also has a good performance in practice. And so this is one of the promises of this approach, as opposed to humans designing algorithms without necessarily looking at the data. And so as takeaways from this overall approach is that reinforcement learning can be very useful in tailoring greedy search or maybe other non-greedy local search approaches to your instances. And the key is to learn features of the objects you're trying to optimize jointly with your search algorithm, or with your, in this case, the greedy algorithm. And this is not an algorithm that's being learned from scratch purely. We're encoding our human knowledge about greedy being a good algorithm in the training of this reinforcement learning agent. And interestingly, some novel strategies emerge. And so this direction has been really, there's lots of progress on this front since we published this paper. And so we used a certain type of graph neural network, which was based on message passing, whereas Ecole et al. Also recently showed that you can use transformer architectures, which have been very successful for language modeling tasks, and which try to represent pairwise interactions between nodes in a more expressive way. So they've used those very successfully to solve a wider range of routing problems. So not just the TSP, also the VRP, the vehicle routing problem, stochastic variants of that, etc. Thanks to this nice use of the transformers architecture. Also, people have looked at other types of problems, again, vehicle routing, also combining this learned strategy with some kind of tree search, so hybridizing a greedy heuristic with a more complete approach to try to improve over the greedy. So this has been done in the paper by Lee et al. And also another interesting direction has been, here looking at scheduling. So similar kind of to the data center resource management type problem that I looked at, but where the objective function is not like a simple sum of the size of the cover, like in the vertex cover case, not a function that you can analytically write out, but maybe a black box, very complicated nonlinear function. So in this paper, it's kind of the execution time of certain jobs that have been scheduled on a very heterogeneous cluster architecture. So it's not something you can compute, but really something you can only observe. So really this fully leverages the power of reinforcement learning in these domains where the reward is a very complicated function. And so beyond greedy algorithms, people have also been looking at kind of local search type procedure. So in this paper, Chen and Tian look at modifying what they call local rewriting, which refers to kind of modifying bits of the solution. So for example, for a 0-1 solution, flipping some bits in a specific way and learning how best to transform a solution into a better solution. And so going back to the question I posed early on in the tutorial in part 1, can machine learning algorithms learn to design combinatorial optimization algorithms? And so what we hope to convey going forward is that, yes, machine learning can help tailor combinatorial optimization algorithms by kind of filling in the gaps that humans may miss by looking at historical data. And so I talked a lot about heuristics and improving heuristics, but as you see, even for this max cut problem, our method in blue still has some amount of error or distance to the optimal. So it's not really optimal. And if you care about finding optimal solutions, a heuristic, any heuristic might not cut it. And so in the next part of the tutorial, my co-presenters will focus on exact solvers for integer programming, which have improved dramatically over the last decade or two. And this is one such illustration of that with the Gurobi solver, also a common integer programming solver, which has seen a speed up of up to 60x, so roughly 2 orders of magnitude over the past few versions, so the last few years. And so we will look more at how we can improve exact solvers with machine learning. Okay. So I'm happy to take some questions.
Yes, Elias, we have a question from the chat. So Wheeler is asking, how can we get some assurance that the training instances will be similar in the appropriate way to the production instances?
Yeah, excellent questions. Thanks for that, Wheeler. Yes, this is a very tricky question, and actually I think the community is still working on ways of addressing it. So I would say typically for experimental evaluation in our papers and others' papers, we've used certain synthetic generators, which kind of guarantee that training instances are similar to testing instances. And the most we've looked at in terms of generalization or transfer learning is to train on small vertex cover graphs and test on much larger ones, or ones that come from a different graph generator, so kind of a different structure of the graph. But your question is very fair, and I think this direction of, and I think Andrea will talk about that as a future direction towards the end, this kind of robustness or transferability is a very important research question.
And we have another question from Jerry. Mm-hmm. So he's asking, local rewriting is your terminology for iterative improvement methods like NOPT?
Thanks, Jerry, for that. So that paper is actually from another research group, but I think the kind of local rewriting they're thinking about is, yes, similar to the NOPT type of strategy in the TSP. Yes.
Another question from Vincent. how trivial is it to extract the kind of heuristic that it learned to apply? Does this depend on how understandable the features are, the graph embeddings? So I think it's about interpretability.
Thanks, Vincent. Yeah, it is quite tricky. So I can tell you, I can admit that for this nice GIF that I showed you, the visualization, we've had to kind of look at a bunch of them and try to say, oh, there seems to be a pattern here. And there seems to be, some underlying strategy that is being learned. But in general, as with a kind of complicated deep learning model, this explainability or interpretability aspect is still quite tricky. Yeah, another interesting direction would be to kind of constrain the space of learned strategies to obtain more interpretable one that can be implemented very easily, maybe without any learning. Thank you. Maxime, I'll stop my share so you can.
Yes. And I will start mine.
Cool. Yeah, we'll be monitoring the Zoom chat as in the first two parts. So please ask any questions there.
Okay. Should I start right away?
Can you remove the small Zoom thing in the top right corner? Are you able to do that? Yeah, okay, I guess.
I'm not sure I can do better than that.
Okay.
It's okay?
Okay, yeah, and I spotlighted your video so people should see.
Okay, so welcome back, everyone. My name is Maxime Gasse. I'm a researcher at Polytechnique, Montréal, Canada. And I will talk during this third part of the tutorial. So this part of the tutorial will focus on hybrid approaches, which are aimed at improving exact solvers using machine learning. So in order to obtain theoretical guarantees in your optimization process. So in order to talk about exact solvers, in this part of the tutorial, we'll focus on MILPs, mixed integer linear programs. So mixed integer linear programs write down as follows. You have a linear objective, which you want to minimize for. So you minimize over the x object. X is a vector here. And you want to minimize this linear objective subject to a set of linear inequalities written down here. And also you have an integrality constraint, which is that some of your decision variables have to take integral values. So it can appear that this kind of optimization problem is kind of limited, like you can only have linear constraints. But it's actually it covers a very wide range of applications. A lot of industrial applications can be expressed as mixed integer linear programs. So it's a very versatile tool in combinatorial optimization. And the vast majority of commercial solvers are aimed at solving this kind of problem. And what is annoying is that those problems are in general NP hard. But still, there exist exact algorithms to solve such integer programming programs, such as the branch and bound algorithm. So those algorithms still have a worst case exponential complexity, but they work very well in practice. So the branch and bound algorithm can be considered as the workhorse of combinatorial optimization. It's been around for decades. It's been used in many, many industrial applications successfully. Even if it has worst case exponential complexity, it is very efficient in practice. People have made it efficient with a lot of engineering effort. So it's really the go-to algorithm if you don't know what to use to solve a mixed integer linear program. So how does it work? So if you go back to our formulation for a mixed integer linear program, and we take a small example in 2 dimensions, you can visualize it as follows. So we have 2 variables, x1 and x2, over which we want to search, to optimize. Those variables are constrained within a convex polytop due to the set of linear inequalities in our problem. So you have this nice convex polytop, and then inside this region, you want to look for points which take integral values. So you only want to look for those black dots inside this region. Your objective function is a linear function, so it's just pointed here to the right. And you want to find the best integer value for that function. So in this example, it would be that point, probably. But how do you find this solution, and how do you prove that this is the optimal solution of your problem? So it's hard to do for a MILP, but something you can do when you have a MILP is solve the linear program relaxation of your MILP. So say that you relax your integrality constraint, right? You consider now that all variables can take continuous values. Then your problem becomes easy to solve. There exist efficient algorithms to solve this kind of problem, such as the simplex algorithm. If you solve the LP, you will end up with a solution at one of the vertices of your convex polytop, like here. And it provides you something nice. It provides you a lower bound to your original MILP. So you know that because the solution of your LP is here, it has this value, there exists no integer solution better than this. So you have a lower bound to your original problem. Okay, nice, but you still don't have solved your problem. One situation in which you may have solved your problem is if your LP solution, by chance, satisfies your integrality constraints. In that case, you would have solved your problem because you have both a feasible solution to your original problem and a lower bound which matches that solution. So you would have solved your problem. But you have to be very lucky for that. In practice, it never happens. So what can you do? Here comes the branch and bound algorithm. So how it works is very simple. It can be summarized into this sentence. You will take your LP, your linear program relaxation, and you will split it into recursively. How do you do that? You pick a fractional variable. So say a variable in your LP solution was given value 3.62. In order to make that variable integer, you can split your LP in 2, and on one side, you will constrain that variable to take values less or equal than 3. On the other side, greater or equal than 4. Because you know that all the values in between, they're not integers, so there will not be any solution inside this range. Visually, it goes as follows. So you take your LP. Your previous LP solution was around here. And you split this LP in 2 using, in that case, variable x2, less equal than 3 or greater or equal than 4. And you obtain 2 new linear programs. Then this gives you a tree. So you see you have the original LP at the top, and you have 2 new LPs when you split your LP in 2 parts. you solve each one of those LPs, each one of those leaf nodes, and you have a nice property here on this tree. The minimum values of all the LPs at the leaves gives you a lower bound, right? You know that the best that you could get with all of those LPs combined is this value. So you know that there is no feasible integer solution better than this. So when you did split your LP in two, what you did is that you lowered the lower bound of your original MIP. So you improved the lower bound of your MIP. And you can do that recursively. So say I pick now this node, this big LP at the bottom, and I split it again using variable x1. I have two new LPs. And here I'm lucky. The LP on the left, when I solve it, I have a solution which is also a solution to my MILP. The variables satisfy the integrity constraints of my MILP. So I found a feasible solution to my original MILP. Maybe not the optimal one, but I found a solution. And this is an upper bound to your MILP problem. You know that there exists at least one solution with this value. And so what happens now is that due to this upper bound, you can discard all the LPs which have an optimal solution smaller than the upper bound. Because you know that in this region, there is no way that you will find a feasible integer solution that will improve upon the one that you already have. So the only region of interest now is here, in between the lower and upper bound. And you would like either to find new integer solution in this region, or you would like to prove that this region contains no integer solution. So you keep branching, you keep running branch and bound. You take this guy and you split it in two, left and right. It appears that the right LP is infeasible, right? The space is empty. And the left LP, you solve it, it gives you a new lower bound. You tighten your lower bound again. So you're not done yet. You can still split this guy. You do that. And you find that your lower bound now is actually your upper bound. So you have both an integer solution to your problem, and you have a guarantee that there exists no better solution to your problem. So what just happened is that you solved your MILP to optimality. You have a certificate of optimality for your MILP and an optimal solution. So this is bunch and bound in a nutshell. So to summarize, bunch and bound is about taking sequential decisions. You select an open leaf of the tree, and then you select a fractional variable to split that leaf into. Then you select a new open leaf, and then you select a new fractional variable to split that leaf into. And something I didn't talk about is that those decisions are actually arbitrary. Whatever decisions you take here, you will still build a bunch and bound tree and you will end up solving your problem. But if you take good decisions or bad decisions, you will end up solving your problem faster or slower. So those decisions are actually crucial to have an efficient algorithm. The stopping criterion for this bunch and bound algorithm is either the one I showed you when your lower bound equals your upper bound. In that case, you have an optimality certificate. It could also be that there exists no feasible solution to your problem. In that case, you end up proving that the whole LP space does not contain any integer points. So lower bound equals infinity in that case. But a nice property of those exact algorithms is also that you can stop at any point. You can do early stopping after, say, 30 minutes. Or you can do early stopping when you have a guarantee that the solution you have cannot be improved by more than 1%. Say. Maybe it's enough for you. Maybe you don't need to solve your problem to optimality. If you have a guarantee that there exists no solution that could improve more than 1%, maybe it's good enough for you. So those exact solvers really have this nice property. So yeah, to summarize, you take those decisions, it will build those curves, like upper bound is gonna go down, lower bound is gonna go up. up to the point where the problem is solved. And the way you take decisions sequentially will affect the way this lower bound will go up fast or slowly, and the way this upper bound will go down fast or slowly. So to have an efficient branch and bound algorithm, you want to make good decisions. But I only talked about branching, but in exact solvers, in the actual implementation in commercial software, many other things happen. A lot of other stuff happen at each leaf, which can be considered a submilp. So let's talk about that. Besides branch and bound, you also run what is called primal heuristics. So what's a primal heuristic? A primal heuristic is any routine, can be an algorithm, it can be whatever, any routine that will look for feasible solutions in any way possible. It can be a genetic algorithm, it can be a taboo search or whatever. And you may decide to run such algorithms at some point in the tree on one leaf. You think there may be a good integer solution on one leaf, you just spend some time searching for it. So you run those primal heuristics once in a while. Then, of course, you have an algorithmic decision to make. When do I run those heuristics? Which heuristics do I run? If you run too many heuristics too often, you will just end up spending time for nothing. And it's going to cost in terms of time at the end. So you would like to run the good heuristics, the one which have good chances to succeed at the right moments in the submilps, which you think might have an optimal solution in them. So this is a new decision task inside branch and bound. Another component of branch and bound solvers is cutting planes. It's actually a crucial component of branch and bound solvers. So how does it work? There are actually routines and algorithms that can probably provide a new linear inequality for your problem, which is guaranteed to not remove any integer solution. So say this is a valid cut. So there are ways to generate such cuts, which are gonna tighten your LP relaxation. They're gonna improve the bound of your LP without removing any feasible solution for your MILP. So when you combine cuts with branch and bound, you obtain what's called the branch and cut algorithm. So exact solvers are more branch and cut algorithms, actually. And then, of course, you have a new decision to make, because there exist routines to generate cuts, but maybe you don't want to add all the cuts that those routines can generate. Some cuts are useless, are not very good. Some cuts are redundant. Some cuts maybe are not good by themselves, but when you do a special combination of cuts, they will prove extremely good. So the decision here is to select which cuts to add to the LP. You do not want to add all the cuts, because then your LP will become too heavy and it will lead to numerical instabilities. So new decision tasks inside exact solvers. Another important component of the solvers is preprocessing. So preprocessing happens before you even start the branch and bound process. Like, you are given a MILP, maybe you can simplify the formulation of the MILP. So some stuff that can be done is that there exist routines, again, which can detect that some variables have to be fixed. Like for some variables, it is trivial to show that this variable can be fixed. Or maybe you can detect that some constraints are redundant. So you can run some routines to simplify your problem this way, and then the solving process will be faster, just because you have a smaller problem to start with, a simpler problem to start with. And then, of course, many algorithmic decisions here. Which routines do you want to run during preprocessing? How many times? You don't want to spend too much time running those routines if they are not successful. So a new task inside exact solvers. So as you may have guessed, there are many tasks inside exact solvers. I will not detail all of them, but basically exact solvers are an algorithm in which you run sequentially, and at some points you have to make decisions. And there is no clear theoretical understanding of what are the good decisions to take. So I talked about node selection, variable selection. Of course, there is also cutting planes, primary heuristics, pre-processing. You could also think about simplex initialization. The simplex algorithms, which is used to solve LPs, start from some initial point. If you start from a good point, you're going to solve LPs fast. If you start from a bad point, you're going to solve your LPs slowly. So all of those decisions have to be made at some point. And something specific also to exact solvers is that there is no clear way to say which decisions are good, because there exist many evaluation metrics. One very natural metric is solving time. You want to solve your problems to optimality as fast as possible. So that's a very natural metric for solvers. But sometimes it's not a good metric. If the problem that you're interested in would take a month to solve, then there is no way you're going to solve it in practice. So maybe you don't want to minimize the solving time, but maybe instead you just want to close what's called the primordial integral. You want to make the upper and lower bound meet as fast as possible in, say, 1 hour of time. Or maybe for some problems, you just want to prove optimality. So maybe you're only interested in the lower bound going up fast. And sometimes you cannot really prove optimality. So you're only interested in bringing the upper bound down fast, which means you are only interested in providing good feasible solutions fast. So in that scenario, you would actually go back to an approximate algorithms, same as the ones Elias presented in the previous parts, where you don't have lower bound, you don't have guarantees. You just want to find good solutions fast. So there are many metrics to evaluate branch and bound solvers. So given those metrics and those decision tasks, how do people design policies? How do you design branch and bound solvers? And this will be the next part. How to take good decisions inside exact solvers. The first way to do it is method A. Think hard about it. So this is what people have been doing for the last decades. This is a traditional way of doing stuff. You have a problem, you just think about how to smartly address your problem. Here is an example from 2007. This is a comparison of different ways to do branching. So the variable selection problem. So at some point you have a score for each of the variables, which consists of 2 scores, the scores of the left children and the right children, and you have to combine them. What is the best way to combine them? Well, it appears that if you do a search like this, you just evaluate on some benchmarks. So this is what they did. They came up with, oh, we could take the minimum, we could take a weighted sum, we could take the maximum. So people just compare some clever rules. And in that case, all of those rules, they do worse than the product function. So it turns out that on a set of benchmarks, the product function to produce branching scores works the best. What you see here is the branch and bound tree size. So it turns out that if you take the product of the scores, you will produce smaller trees. So consensus came up that the product is a good way to make decisions for branching. So this is how those decisions have been answered over the years, traditionally in exact solvers. You just come up with some clever rules, you compare them empirically on a set of benchmarks, and then you decide, oh, this one is the best, it works best. And as you see, it's not so far from machine learning. It's hand-designed machine learning. So as a result, in state-of-the-art solvers, most of those decisions are taken via hard-coded decision rules, which have been tested over the years and which work well on average. So for example, for variable selection inside the skip solver, the variable selection rule is named reliability pseudo-cost branching. For node selection, it's called best estimate search. For primal heuristics, what is done is that you just run those heuristics at a certain frequency, and that's it. It's not super clever, but it works. Here is an example which I like. How do you do cutting plane selection inside the solver? Well, it turns out that it's done via a magic formula, which is a linear combination of you compute what is called the objective parallelism of each cut. So how parallel is it to the objective? You compute some directed cutoff distance. You compute the efficacy of the cut, the integral support of the cut, how many integral variables are involved in the cut. And then you do a linear combination with those values. And you pick the best cut this way. So it turns out that this has been tuned and it works well on average. But as you can see, it's just a linear combination. It's kind of dumb. So maybe you can do better than that. And if you think about commercial solvers, how they decide on those decision tasks, each one of those solvers, IBM Cplex, Gurobi, or Fico Express, they have their own secret recipe, right? They are closed source. They spend some engineering effort to design good decision rules. And this is what makes them competitive or not competitive. So this is the traditional way of solving those control problems. What about method B, learning automatically from data? This would be amazing. Instead of spending hours and efforts in engineering to design clever rules, maybe you can just learn from data. Maybe you can just exploit the statistical relationships between a set of instances. So you assume that if you learn good decision rules from a set of instances, those decision rules should still be good for similar instances. This is the basic assumption. It's a reasonable assumption. And it actually makes sense, as Elias mentioned in his talk. In many applications, many industrial applications, people solve very similar problems every day. You solve a logistics problem every day. The road networks remain the same. Your customers didn't change so much. So we believe there is a lot of redundancy between the problems that industrials solve every day. And this is not really exploited by traditional solvers. Also, some encouraging things are that machine learning already has been a game changer in many domains. In image processing, you could not even think about not using a neural network. In natural language processing, it's the same. Medical imaging, recently with game playing. So what about combinatorial optimization? Maybe machine learning can also be a game changer here. And so people have been excited about this idea of learning automatically exact solvers from data. And it's a very exciting and growing field. So as you can see, in the last 5 years, there has been a lot of works in all of those decision tasks which I mentioned. So people are looking at everything here and with promising results. So it's really an exciting field right now. So I explained what the problem is, taking decisions inside an exact solvers to improve their performance. But how would you do that with machine learning? The best way to apply machine learning tools here is to have a standardized framework in which you can just cast all the existing machine learning algorithms. And the natural framework is the MDP framework here, using Markov decision processes. So this is a very generic framework where if you're not familiar with it, you have you can think of an agent that takes actions in an environment. based on this action, the environment will go into a new state. It will update, it will change. The agent will observe this new state, and then it will take a new action. And the environment will get updated, will return a new state, and the agent will take a new action. So you can really model a sequential decision process by an MDP. In our case, the state would be the whole state of the branch and bound process of the solver. So you can just think about the memory inside the computer, the program memory of the solver. That's the state. The actions would be, depending on the task that you want to solve, could be variables to select for branching, or nodes to select for branching, and so on. And here an episode would be solving an instance from start to completion. Yes, something to mention is you can also see algorithm configuration, which is just selecting parameters and then running the solver. It also fits into this framework. It would be framed as a bandit problem where there's just one step, there's just one action to be taken, but it also fits into this MDP framework. I'm not sure about time. Elias, could you remind me how many minutes I still have?
So you've spent 29 minutes.
Okay.
So maybe a couple more. Yeah,
okay,
that should be fine.
I'll be a bit fast then in the end.
Cool.
So you have the idea. You can cast all of those problems as Markov decision processes. Once you did that, you can just apply straightforward machine learning algorithms which have been designed to solve MDPs. So two families of algorithms are imitation learning, where you imitate an expert which is too expensive, but takes good decisions. If you imitate it well enough with a machine learning model that will be fast, it can have some useful applications. And the other family of algorithms are reinforcement learning algorithms. So here it's very straightforward. You define a reward function and you minimize it using reinforcement learning. It's way more challenging, but then you don't need an expert. You can really learn from scratch, learn very new decision rules. And it's been very effective at very complex tasks. So maybe it can be effective as well for combinatorial optimization. And of course, if you want to go for machine learning to solve those problems, there are many challenges. So I'm not going to go into too much details here because this is going to be the topic of the next part. So the first challenge, of course, is representation, because here you are dealing with mathematical objects, dynamical structures, the branch and bound tree. You have also a variable size structure. MILFs can have different size. It's hard to find a way to just cast those into a nice representation that you can fit into a machine learning model. So you have to think about new ways to do representation for those objects. You have, of course, the generalization issue. We don't know if machine learning can generalize in the context of MILFs. So, of course, this is related to how you are going to represent MILFs and which machine learning models you're going to use. But this is something to pay attention to. And there is the data challenge. How to design training datasets. Traditionally, MILF datasets have not been built for machine learning. They're not very big. So maybe you can think about doing data augmentation for those datasets. And also metrics. So I presented some metrics to evaluate exact solvers, but maybe they are not very well tailored for machine learning. So could you design nice metrics that would make sense and be suitable for machine learning? That's also an additional challenge to tackle. So to summarize, I hope that I have gave you a good overview of those 4 points. The branch and bound algorithm, which control problems arise inside exact solvers, an MDP formulation, which is going to allow us to solve those control problems using machine learning. And also I presented quickly the open challenges for machine learning. I'm going to take a few, maybe one question now, and in the next part, Giulia and Laurent are going to talk more about these machine learning open challenges and how people have addressed those challenges in the literature.
Thank you, Maxime. So there are currently, as far as I can see, no questions in the chat. So maybe in the interest of time, we can move to the next presenters, and then after that, there'll be a break. And so if there are questions then maybe you can answer them.
Yeah, perfect. So I'm going to stop sharing my screen.
Okay, Giulia's turn.
I'm going to share. Okay, you see my screen?
Yes.
All right then. So yeah, welcome to part 4 of our tutorial. I'm Giulia. I'll guide you through the first half of this session, and then Laurent is gonna take over after me. So yes, for people that are maybe joining now or will rewatch this later, in part 3, Maxime gave us an overview of the mixed integer programming framework and the branch and bound algorithms. And he also exposed this MDP nature of various control tasks that happen within exact MIP solvers. So overall, what we're doing here is we are interpreting machine learning as a new tool for MIP computation, which we can use to improve or automatize some of these algorithmic decisions, which are often heuristic, and to augment the solver capabilities to reach more sophisticated and flexible outcomes. So this is a really new, exciting field of research, and the MIP setting in particular provides very challenging things to think about for machine learning as well. So in this session, we will look at some of these challenging themes in the field, and we see how they are interpreted and addressed in the literature. What we identified are four themes: representation, generalization, data, and metrics. And we will mostly focus on learning to branch works. That's because we like those works, and also the literature is very rich in this area. So when we say learning to branch, we really refer to what Maxime explained as branching or variable selection. So again, when we're solving a MIP problem with branch and bound, we are repeatedly relaxing the problem at every node, every leaf node of the tree. And when we solve this relaxation and the solution is fractional, what we want to do is we want to select a variable to create 2 new child nodes to be added in our search tree. And this learning to branch, this operation of splitting the tree is what's called branching. And of course, it fits very well in the MDP paradigm of having these underlying MIP solvers that carries on the optimization and that is querying a machine learning predictor for some action, for some decision in one of its subroutines. Okay, so let's start with representation, features and models to be used. When you have your MILP formulation, it's just a raw optimization problem which you're trying to minimize this linear objective function. You have some set of linear constraints, and some variables are required to be integer. So you definitely have instance-specific parameters that you can look at for your representations, but there's much more to that. So for example, you could think about exploiting somehow the variable constraint structure that is given in the matrix A. There's more information that you can gather in the node relaxation during the branch and bound tree. There's global information coming from the tree structure itself. There might be other algorithmic clues hidden here and there. So where do you look at, and how do you decide how to represent your task? Well, the truth here is that there is no natural representation of MIPS or branch and bound, and that's like in contrast with respect to other typical machine learning applications like image recognition, for example. So the challenge here in the MIP setting is really to capture the relevant information for a given task that you want to address in MIP solving. And this often will require trading off the expressiveness, conciseness, and the scalability of both your input features and the machine learning models you put in place. So let's look at this example from the literature from Marcos Alvarez and co-authors. This was one of the first works that appeared in Learning to Branch. What these authors are proposing was a very basic supervised approach using extra trees on strong branching scores. And the input features that they derive are directly coming from manipulation of the instance parameters. They're careful manipulation of those parameters, actually, with the aim of describing a given fractional variable at a given node of the tree. And one important distinction that the authors put in place from the start is that between static and dynamic features. So they recognize that there might be some features, some characteristic to the problem that are inherent with the structure, with the formulation itself, with the raw milk formulation itself, and thus will not change during the algorithm. And then on the other side, there are some dynamic information that are changing throughout the branch and bond algorithms at different nodes and so on, which we should also look at in order to take proper decision and to train well our machine learning models. Interesting guidelines also for representations that are identified first in this paper are that your representations should be independent of the size of the problem you work with. They should be invariant to irrelevant changes in the MIP formulation. So for example, invariant with respect to permuting variables or constraints. And they should be independent of the scale of your parameters. And that's because you ultimately want this representation to make sense across different instances. So those guidelines, these properties for representation are still very valid. I think they're non-trivial for machine learning research as well. And these are very valid, and though these initial ideas actually evolved much in the literature in the course of the last couple of years. And I would say especially in terms of the machine learning model that we use nowadays. So we have more mature models right now. This is an example from Gasse and co-authors. Here the authors are really exploiting the structure of the constraint matrix of the MIP using a graph neural network. So that's like a very powerful model, which they pair with basic feature representation at the node of this GNN. And they use it to infer a branching rule, a new branching policies that could work across problems that are indeed sharing this combinatorial structure, which is exposed in the constraint matrix. And a same GCNN architecture is also at the center of a more recent work by Gupta and co-authors. And here, the crucial theme is this time accuracy or this scalability trade-off. So the question is, can we approximate the performance of this powerful GPU-based GNN with cheaper MLPs that actually are running on CPUs? And the authors come up with some hybrid approach. So they also try to explore hybrid representations for MIPS to put in place a new, to learn a new branching rule that balances this predictive power and exploiting structure with more computational constraints. So a lot of possibilities in this sense. The second challenge that we identify is generalization. So of course, exploiting some combinatorial structure makes sense if we want to repeatedly solve the same problem over and over, but that should not limit our thinking about generalization. It's not the only way to think about it. The challenge in the MIP setting is really still thinking about how to measure generalization. We don't have a single or definitive meaning for it yet. Also note that this generalization goal that you might set up for yourself when you try to integrate machine learning in the MIP framework also will interact with the level at which you think this integration will take place. And those things will influence in turn your representation design and the choice of which machine learning paradigm you would use. So let's look again at some use case. This is a paper from Khalil and co-authors. And here again, it was a supervised learning framework for learning rankings of the fractional variables at a given node to decide the one on which to branch. The idea here was to basically create policies that were instance specific somehow. So to collect data from the first theta nodes of a branch and bound run, and then train a policy that could be then deployed for the rest of the branch and bound run, the same run. So the idea, the goal was really to speed up a single run and generalize to the rest of the search, having observed only the first part of it. So this is a single, if we want a generalization to a single instance every time. And of course, when you want to move from single to multiple to many instances, then the first step would be to look at families of similar instances. So again, that's the work of Gasse and co-author, but also the one of Ansknet and co-authors, which both aim at generalizing within a special class of combinatorial problems. In the case of Ansknet and co-authors for the TSP, while Gasse and co-authors explore different special classes of problems. So in both these works and in many others in the literature, the generalization is measured on synthetic instances from the same distribution. So technically instances for which you have a generator. And the policy is tested on instances that are bigger in size compared to those on which you perform training. And this might be a good way. It definitely comes with some inherent limits for more expensive models, like actually the GCNN one that we saw already. So there's one more recent work, which I'm actually co-authoring, that tries to go even beyond this generalization within families and to learn a policy that could generalize to generic MLPs without putting any restriction on the structure or the size of the problem. And to do that, what we do is we try to avoid an explicit use of the parameters or of the structure of the metrics, but instead to represent something alternative. We try to represent the branch and bound search tree. So we have new input features and new machine model, a new DNN architecture to process these features. So the idea behind the work is to somehow increase the inference of higher level branching factors that might be shared. And at the same time to decrease the likelihood of overfitting to superficial regularities, which could instead be exposed if we were to be using a structure like the GCNN or other input features that are more related to the parameters. So a remark for me is maybe that even for learning to branch, which is this single task that we will focus on and Laurent will also focus on next, it's a single task, but there are many options for representation and generalization. But even there are many options in the way that you can interpret this integration of machine learning in the MIP solver for the task of learning to branch. So these approaches can range from learning to select from a portfolio of non-branching rules, so basically just learning a switch heuristic, to learning instead convex combination of existing branching scores. We've seen other works that are trying to use supervised learning or imitation learning on existing branching rules. And finally, there are very new, more recent work that are trying to use reinforcement learning to learn from scratch new heuristics, new policies without like any link to previously known ones. So really my take home is that this integration of machine learning and MIP can happen at various levels, and there's a lot of options to explore. Laurent, you'll take it.
Thank you so much, Giulia. So let me just start the screen sharing.
Great. Yes, we see your screen, Laurent.
Yes, good. Thank you. Okay, so I'll move right along. So I'm Laurent Charlin. I'm a assistant prof at HEC Montreal. And so Giulia talked about sort of the first two themes, which were representation and generalization. I'm going to talk about the last two themes, which are data. So data and metrics, sorry. Okay, so let's begin. So of course, when you think of ML algorithms, one of the first things you think about is data, right? What am I going to train my algorithms with? And when you think of ML algorithms for MIP solving or for combinatorial optimization more generally, you have to realize that these two types of algorithms consume data very different. So you can think of MIP solvers such as Cplex or Skip as being these sort of generic algorithms that really were made to solve lots of different types of problems or heterogeneous instances. Whereas, of course, if you think of ML models, you typically must train them on representative data, right? So they'll most likely will only generalize to the distribution of data they've been trained on, okay? And so that means that although there are many possibly learnable problems within combinatorial solvers, really there does not exist much what I would call machine learning data sets simply do not exist. And when I think of a machine learning data set, I simply think of a set of pairs of features with a label. Okay, and so if you think of using machine learning here, I think the big challenge is giving a task. How do you create large scale and realistic data sets? And there's been lots of progress in this over the last couple of years. And my take on what sort of where we are now is that if you're looking at homogeneous instances, right? So if you're looking at instance of a particular problem, for example, a TSP, then for some of these problems, there are generators. And you can use generators to generate, of course, synthetic data set that you can then use for learning how to do learning to branch or other popular tasks. If you're looking at heterogeneous instances, right, so instances for many different problems, then you can repurpose effectively standard MIP benchmarks such as MIPLib. One caveat though here would be that for each type of problem, often you'll have a very small number of instances, okay? So before going on to use cases, I thought I would just talk a little bit about data set and data set collections, just to make things very crisp and clear. So when I talk about a data set here, I really mean a set of MIP instances that are split into a training set and a test set. A data set can be composed of a single problem, for example, the TSP, or a set of problems. And this is what I would call homogeneous, a single problem, or heterogeneous set of problems. Then there's really sort of two modes in which you can gather data. You can gather data for supervised learning, including imitation learning, where here the idea is you might want to run the solver with a particular set of heuristics and record what the solver is doing. Okay, and in this case, of course, the state, which can be something to do with the solver and the problem definition, you can see that as being features, and the decisions that the MIP solver is taking, you can see these as labels, right? So for example, decision could be which variable the solver decided to branch on. Of course, another mode of interaction is reinforcement learning. We've talked about it, and Maxime has talked about it, for example, in this part. And here you would think of a slightly tighter integration between the learning and the MIP solving, where you can think of the MIP as being this environment in which your agent is acting and trying to find optimal policies. Okay, so this is it for data sets. We can now move on and look at particular use cases and types of data set that they've used. So you'll notice that lots of these papers are actually very similar to the ones that Giulia discussed. Not all of them. This is by design because, of course, in this part we're going to focus on data, and then I'm going to focus on metrics. So in this paper called the Machine Learning Based Approximation of Strong Branching, they use two different types of do two different types of studies. In the first one, they randomly generate instances, and these instances are use combinations of constraints from known problems, such as set covering, multi-knapsack, and so on and so forth. To give you an idea, the size of the problems they generate are in the hundreds of variables and constraints per instance, and this is pretty typical of what people are trying to solve these days. There's a few recent papers that are trying to go much bigger than that. And then in terms of size of training set and size of test set, they think of here 25 instances and 50 instances, right? So not a very big instances, not very big train and test sets in this particular case. And then just to give you a flavor, these numbers, of course, aren't very important. I just wanted to show you. So typically then what you would do is you would say, I'm going to train on a particular type of problem, maybe BPSC, doesn't really matter what that means. And then I would report accuracy, or I would report some metrics, and I'll talk about metrics later, on some test set. Okay. So that's one thing they do. The second thing they do, the second study B here, is they look at 44 instances from MIPLib and MIPLib 2003. And so in this case, they're looking a lot more at heterogeneous instances through these standard MIP benchmarks. So that's one example. Another example I wanted to mention was the work of Elias, published in AAAI a few years ago. Here, like Giulia went over it, the basic idea is to frame the problem as a learning to rank task. And of course, here, one thing they're able to do is they're able to look at heterogeneous data sets, even if they're able to look at heterogeneous data set, because they effectively learn in the first part of the solving, right? So if you think of solving as this iterative process, they're actually learning in the first part of the process, and the second part, they're using their learned model to be able to make predictions about optimal decisions. Okay, so that's another example. Of course, as I said, there are recent approaches that are trying to do something similar, but with reinforcement learning. Here, there are in this MDP framework that Maxime nicely outlined, and the reward would be, it could be different things. What they were aiming to get at in this particular work was small trees, and so they said each step you have to make, each action you have to make, you actually get a negative reward of -1. And here, regardless of whether you're in supervised learning or in reinforcement learning, the same types of problem can be useful. And so they looked at standard problems. I believe these were all synthetic cases, so they had a generator for this, and the size of the problems were also quite similar. Okay, and again, the type of results you would get is that in this particular case, for each data set, you get a set of results where here rows correspond to different methods they wanted to compare against. Okay, so this is a brief overview of some of the data sets that have been used in tasks such as learning to branch. We can now move on to metrics. So of course, the ultimate metric, in a sense, is how fast can an instance be solved. Okay, this is what Maxime also mentioned, but as Maxime mentioned, there's a few caveats with this particular metrics. And especially if you think of it in terms of machine learning, then the first question you might have is, how would I actually directly optimize? Okay, so we know that machine learning approaches usually tend to do really well they tend to do well if they can optimize what you fundamentally care about. Okay, so here what I'm saying is, if what you fundamentally care about is how fast an instance be solved, you'd like to be able to optimize that. This is of course very difficult, especially since in scenarios and tasks such as learning to branch, the ML prediction is really making this super local decision, whereas how fast an instance is solved is a very global, sort of a global metric. Okay, so that's one thing. Another thing, of course, is hardware dependency. So how fast you can solve something depends on the type of hardware you're looking at. And of course, now if you're going to use deep neural nets, often the go-to method is to go in GPU. So then you're going to compare a method using a GPU with a method that's actually using a CPU, and then it's a little bit unfair. When is that comparison? It's a bit unclear, sorry, when is that comparison fair and when it's not. The third thing I would mention is scientific progress is sometimes better measured through other metrics, right? So a good example of that are primal heuristics. There is, of course, a relationship between how good a primal heuristic is and how fast your solver will be. But in general, you might want to focus on sort of subset of the whole problem, and these dictate different types of metrics. So I would say in general, if I was to frame that as what is a big challenge for machine learning regarding metrics, it is to find optimizable and useful metrics for combining ML models and solvers, where I think of optimizable as being something that you can use for learning, right? So at least naively, deep neural nets will require smooth functions, functions you can take the derivatives of, which isn't necessarily the case here. And of course, you want some also useful metrics. And that means, for example, metrics that can correlate with the final objectives and metrics that sort of reliably measure progress that you're making. In the state of affairs, I think there's a few standard test metrics that people have been using. I'll show you examples in the next couple of slides, including time, including size of the tree, and including primal gap in certain situations. And in general, though, there is little integration, especially for tasks like learning to branch, between the ML training objective and the final MIP test metric that you care about. Okay, so let's look at a particular example of a paper. This is also one that Giulia covered. In this paper, there's two levels of evaluation. In the first level of evaluation, the authors compare different learning methods using ML metrics. Okay, so here this was a supervised or an imitation learning task. And so there is a ground truth label, and basically what the authors are comparing is for each row, that these are different methods, the accuracy on a test set of these different learning methods. Okay, so this is nice, but of course it does not tell you how these sorts of gaps, say between 57 and 65, how do these translate to on your final MIP metric that you really care about. So then there's a second level of evaluation, which looks at roughly the same methods, but of course you can now also include non-learning methods. And then you can compare. And here there's sort of three levels or sort of three metrics that are used, sorry. The first is time. Okay. The second is how many wins in terms of time. So you can think of that as sort of a binarized version of time. And the third is number of nodes. So in effect, effectively the size of the tree. And you see, at least for the learning method, there's a reasonably good correlation between time and number of nodes, but that's not always true, especially if you compare learning methods to non-learning methods, which can act in very, very different ways. I said, of course, that time is perhaps somewhat unfair, especially here where you're comparing this method, the GCNN, that's running on a GPU with other methods that don't have access to GPUs or any types of specialized hardware. And so then in follow-up work by a similar subset of authors, they were able to basically rerun something that was very close in spirit to the GCNN, but on a CPU. And you see the results are similar. And in this particular case, the results on CPU even seem a little bit better, right? But of course, this requires thinking. Okay, so moving on and talking about another metric or two. So of course, I've said that in general, you can care a lot about time, but in specific instances, time may not be what you care about. And for example, right? And so the point here is for other problems, there could be other metrics that are better tailored to the situation you're in. So for example, if you're in a situation where finding a feasible solution is very important, that could be because you're in a domain where feasible solutions are difficult to obtain. That could be because quickly finding good feasible solutions can be useful for decision making. And so what you can do in cases like this is to look at the primal integral. This is something that Maxime mentioned. I thought I would just go back to this picture, which looks a lot like the one from Maxime, but is actually from this paper. So here effectively what you are measuring is how quickly you find good solutions. And to do that, you measure the area under this curve, where the y-axis is the primal gap, And this is normalized, so that's why it's between 0 and 1. And the x-axis is time, okay? So effectively, you're saying something like, right, how quickly am I going to find good solutions? And you know, of course, that when you get to 0 here, you've found the optimal, and you start, we normalize such that you start at 1, okay? So this is one thing you could do, which is particularly useful when you care a lot about finding good feasible solutions. In very recent work, in a paper from that was recently pushed on arXiv by DeepMind, they've looked at something similar, except that they care not only about finding good feasible solutions. So instead of looking at the primal gap and the primal integral, they looked at the primal dual gap. And so this picture that you have at the bottom right is they compare their method to SCIP here, which is just a MIP solver, according to this primal dual gap average across a number of problems. Okay. Another thing, of course, which is sort of, or another thing I wanted to point out here is the x-axis a priori should be hardware dependent. And in this paper, they actually propose to calibrate the different machines they're running on. And so you can think of that as sort of normalizing or calibrating time such that comparison across different machines remain fair. And I think that's true across different machines, but not necessarily across different hardware such as GPU and CPU. And then I guess in the spirit of integrating the final objective, the MIP objective, with the learning objective, one way to do this is to look at reinforcement learning. So here's work from a recent paper where they use a RL approach. And the word here is -1 after each action. And this encourages solving the problem in as few steps as possible. There's also other recent work which does something similar, but instead of saying that they want the smallest tree, they care about the primal integral, and so their reward is the negative primal integral. Okay, they want to minimize, they want to maximize this or have a small primal integral. Okay. So a few takeaways from both our parts, and I'll try to do justice to Giulia's part. So Giulia first mentioned representations. Key takeaways here were that there's no natural way of describing MIPs or B task for machine learning, right? So there's space for creativity, and there's been some work on this, but there's definitely space for a lot more. And of course, in all these things, there's going to be this trade-off between expressiveness and scalability for both features and then model. And Giulia also mentioned particular types or the roles of invariances that could be useful. Then if we think of generalization, it's a little bit unclear how to even define this machine learning term in the MIP setting. And it's unclear how to properly measure it for different MIP tasks. Is it across instances? Is it across problem? Is it across sizes of problems? And of course, Giulia also clearly talked about this interaction between ML and MIP can happen at different various levels. And so of course that affects the sort of questions you can ask about generalization. Then I talked a little bit about data. So most of the work we surveyed were people use a combination of synthetic instances with generators and MIPLib. There are also a few papers, or there are also papers that look at real instances. The issue there is often these types of instances are harder to share, right? They're often proprietary, and so they're harder to share with the rest of the research community. And finally, we talked about metric. Really, the takeaway here is that the right metric depends a lot on the problem you're considering. And in general, training with test metric remains a challenge. We saw RL work that looked at some of this, and part 6 of this tutorial actually will study these questions under the umbrella of decision-focused learning. So many thanks for your attention, and I think
awesome.
We're happy to take questions.
Thanks, Laurent. There was one question, and Giulia answered it in the chat earlier. So I think let's take this roughly 8-minute break. If you're able to stick around, Laurent, then people can ask you during the break. And so we'll resume at 10:50 PST. with Antoine. And he's going to talk about Ecole, which is a Python-based software framework for doing this kind of learning in a advanced MIP solver. So Laurent, there's a question in the chat. So Mohit's asking, when we saw the results regarding primal dual gap, do we see the improvements just because the heuristics are faster to estimate with ML, or is there some other intuition as well? So I guess rephrasing is, where are these improvements in this case, in the case of the primal dual gap, where are these coming from? Yeah,
sure. So let me try to answer that. And of course, Elias or Giulia, if you want to chime in, please do so. So it depends. This is sort of very, very paper specific. In this particular paper I was talking about from DeepMind, where they look at primal dual gap, they actually come up with a fairly, or what is somewhat innovative, I guess, architecture to solve this problem. And so exactly why it does better then would depend on the architecture, and would also depend on how you're training this architecture, right? What do you use as an objective to train this architecture? And so I don't think we could say it's just ML versus other heuristics. It's really the model you use in ML and how you optimize this ML model. Elias, anything to add, or Giulia?
Yeah, perhaps I could follow up for that specific case in the DeepMind paper you mentioned, and they had the primal dual gap. They were trying to find a good solution fast and to guide the branching of the solver. So this improvement was coming from one or the other, or both, meaning either you have a very good solution earlier, so this primal integral that Laurent mentioned is improved, or you're also, closing down the search tree faster. And so this primal dual gap takes both of these metrics into account.
Yeah, maybe just to add like a closing remark to this, I guess that's another challenge, like understanding like why your machine learning model is doing eventually better than your MIP solver. So yeah, sometimes we use imitation learning with the idea of speeding up a decision. But often I would say the decision you learn can look pretty different from what you can find in the MIP solver itself. So understanding, so having some insights about what's going on, it's I guess will require a bit more time to understand. Yeah.
Thanks for the question, Mike.
Yes. Okay, you should be seeing my screen right now and my slide.
Yes, perfect.
Okay. Okay, should I get going?
Yeah, please go ahead.
So in this part, I'm going to present a software that we're developing in Montreal, which in a sense is going to be a mirror of many of the things we've seen so far, in the sense that it's going to be the practical implementation of all the theory we've been discussing and the example we've seen. So very quickly, I'm a PhD student in Polytechnique Montréal under the supervision of Andrea, Lodi and Yoshua Benjo. And I'm the lead developer on this project of this library of ours, Ecole. So very briefly, my 2 cents on machine learning for combinatorial optimization and the way that Ecole fits in all of this. So if you think of the traveling salesman problem, most people would think of a problem on a graph and you have to find the shortest route between the nodes. But actually, by definition of NP completeness, every problem can actually be formulated as a TSP. So for us, this is the sign that there is, when we try to solve combinatorial optimization instance, we have to look for something more subtle than just the problem definition, the mathematical problem definition, because in a sense, they can all be equivalent. And actually, if we look at real world application, for instance, a real world traveling salesman problem, depending on the city, we're going to have a distance metric that's going to look very different depending if we're in Paris or in Phoenix. And with machine learning for optimization and Ecole in general, what we want to do is to be able to specialize our algorithm to these different subtleties that we can find in the real world problem. So basically to fit to the problem distributions that are relevant for a specific application. So the first question is, why do we need a library to be able to apply machine learning inside a combinatorial optimization solver? Typically in a lot of the work that has been mentioned so far, combining machine learning with solvers are two very different technologies. And in a lot of what I've seen is that it takes usually months of software engineering before a researcher is able to even run the first experiment. And the result code is usually not well tested, not optimized for speed, hard to install, hard to read for other people, and not very reusable. So this is what we want to bridge with Ecole. We want to provide an easy way to get started on this field with a good API, good default, something that is going to be fast and robust, but at the same time, something that is also extensible, so that we don't want to push too much our own ideas of what this type of research should be. It should enable all the largest possible research on the topic. So our library is written in fully in C++ with binding to Python. So you can install it through Conda like a regular Python package. But if you want to use it in C++, or if maybe in the future there are different languages that we want to support, that's also going to be a possibility. Ecole, the key idea around Ecole is the idea of a learning environment. So a learning environment is a Markov decision process that Maxime has already talked about. So in a Markov decision process, an agent interacts with an environment and on every state takes an action. And as a result, the environment transitions into a new state and the agent receives a new reward and can obtain a reward and can observe a new state as a result. And the goal for the agent is going to maximize the expected sum of future rewards. So we all know the very common OpenAI gym that is used in reinforcement learning. Here, the agent is going to be the neural network or the human that is playing some Atari game. The environment is going to be the old Atari console or emulator, and the action that we can take are the controller that is going to control our space invader spaceship. And we want to maximize the reward that we get to this in the game by just observing the screen as a human would do on a television. And okay, the typical API is built around the idea of an environment. And so when you iterate when you want to interact with this environment in OpenAI Gym, what you do is you start a new episode, so a new game with environment.resets, and then you can transition from one state to another by calling environment.step. As a result, you get an observation, a reward, and you loop over this transitions, these episodes, as many times as you need for learning. Usually it's not or extremely hard to learn a good policy, user-defined policy in one single episode. And we've built Ecole just around the same key ideas that researchers in the community are used to. So we frame also, for instance, branching as a Markov decision process, where the environment is going to be our combinatorial optimization solver in general. So in the case of Ecole, is going to be our solver skip. That's our whole environment. The agent is the policy, the variables selection policy that we want to learn. That is going to select the branching variable. And as a result, our solver is going to be in a given state on every node. And we can observe some statistics of the solver. So whatever information we find relevant for our branching policy. And we need to define some reward that we want to maximize. I'll say a bit more about this. It's hard to find a good reward, but in this example, we'll say that we want to minimize minus we want to minimize the number of nodes in our branching bound tree as a proxy for time. So our API is actually very similar to OpenAI Gym with a few subtle differences. So in the same way, you can see that we're going to start a new episode. So start a new branching bound tree, a new instance to solve with environment.reset. And we're going to transition from one branching bound node to the next by calling environment.step. There are a few differences. So the first one is you can see that environment.reset receives a pass to a problem, an instance definition, because in our setting, there is no point to learning over the same instance over and over again. What we want to do is learn over a distribution of instances. So in a sense, the Markov decision process is parameterized by an instance. So this you give to environment.reset to start with. And you can see that as a result, we get a few more outputs than OpenAI Gym. For instance, we have a reward and a down flag on reset. That is because, for instance, an instance could be solved just on reset without ever branching if it's solved at pre-solve time. We also have this action set that is returned, even though in OpenAI Gym we can have like this observation state space and action space, because in the case of branching, it's actually much more dynamic. It's not that the branching environment has a defined action space. It's not that a given episode has a defined action space. It's on every transition, we have a dynamic number of variables that we can choose from. So here we need that information. We need to know the candidate branching variable on every node to be able to make our decision. So this were the motivation for the change that we have done. And similarly, given a user-defined policy, so something that the researcher is going to implement, neural network, graph neural network, something simpler, or even something without branching, if you want to benchmark against something else. We're going to loop over this transition, this branching bound node, by calling environment.step. We're going to do that a few times to be able to learn a policy that is able to hopefully generalize within our instance distribution. Very briefly, I put a slide for the mathematics of what I've just said. I'm not going to go in through this. It's more for the replay if you want to go afterwards and pause on it. So here we've shown the case of branching with a very specific reward and a lot of things that seems like frozen, but we want Ecole not only to be able to reproduce the current work on learning to branch that exists, but also for researchers to define new environments, new tasks that they think are relevant to the field. So in a sense, if we look at that Markov decision process, all of the environment, the reward and state can be configured by the user. We can easily change basically everything that we collect, that we want to collect from the solver, and also the way that we're going to define the transitions, so the environment. We've done that through composition. So when you create an environment, you actually pass a reward function and an observation function that is going to define what you get as a reward and as an observation. So an observation, because in this case, the state is actually the full state of the solver, and we only observe something out of the state. And in this example, we can see that we can very easily combine multiple reward function into a new reward function, into a function of this reward function. And similarly, here we've decided to pick an observation function that is the graph bipartite used by Gasse et al. In 2019, but a user can choose another one or define a new one to get started with the research. So as an example of what it takes to define a new reward function, it's mostly it's a class with two methods that you have to define. Before reset, that is going to be called every time on every episode before reset, and a method extract that takes the model, so the PySkipUp model in a sense, except our own class for it, we can convert to PySkipUp with no copy. And then you have to return whatever reward you want to return. And this is a pure Python class with no inheritance, no magic. Basically, the environment is just going to pass in the state through that class and return to you the reward. So here we see an example of a skip function that is get and node init LP iterations. And we create a reward function by computing the difference in this metric in between two states. So we've shown that the environment in Ecole is we can customize the observation function and the reward function, and also the information you get in the info dictionary in OpenAI. So if you take all of this information out of the environment, what you get left with is the environment dynamics. So basically, the environment dynamics are the transition probabilities that we've seen in the Markov decision process without any notion of observation or rewards or anything. So to create new dynamics, what you need to define is the way that you get into your initial states, the way you get your solver into an initial state, and you need to transition in step dynamics, the methods, your model, your states from one state to the next. So in branching, for instance, this method will transition from one node to the next. And if you get all these things together, then the environment class will piece all the problem together to see the nice API that we've showcased before. We have also added a collection of instance generator because we realized that it's important for the field to have common generators, and also for researchers to get started. It's also often hard to find instance generator that have code that come with them and that you can easily install. They're very Pythonic. They're Python generators. We have a set cover instance generator, capacitated facility location, independent sets, combinatorial auction. And if whatever parameters are passed do not suit you, you can easily combine multiple ones by just creating a new Python generator that is going to dispatch call to different generators dynamically. So here we see if we take a couple generators, we can toss a continuous coin and then decide which of the generator we're going to call every time we want to generate a new instance. So thank you for your attention. Our documentation is available online on Ecole.ai, and our GitHub is online. We welcome collaboration and pull requests and any question that you can have.
Great, thanks, Antoine. So there aren't any questions in the chat at the moment. So maybe in the interest of time, if you have questions for Antoine, please post them and he will check the Zoom chat. And we'll go on to part 6, presented by Bistra Dilkina. Bistra?
Yep. Hi, everybody. Let me share my screen. Okay. So very happy to be part of this tutorial that gives such a wonderful overview of so much of the exciting work at the intersection of integrating machine learning and combinatorial optimization. And today I will talk about a different aspect of this space, which we call decision-focused learning. So we have already seen some wonderful examples of integrating machine learning into combinatorial solving in order to be able to help us to augment discrete optimization algorithms with learning components, with the idea of speeding up our ability to solve large-scale real-world problems. Well, in this part of the talk, I'm going to focus on trying to go in the opposite direction, where we are trying to infuse machine learning with constrained decision-making. So we're going to be thinking about how learning methods can incorporate information about the combinatorial decisions that they inform downstream, right? So we are going to be putting the combinatorics into the ML part, as opposed to the ML part into the combinatorics. And as most of you know, many real-world applications involve a common template where we have some observed data. Based on this data, we need to make predictions about parameters that we care about. And with these parameters in hand, we need to make decisions in the real world with our whatever constraints our organizations have. And so this is really a very common setting. And in most of those settings, the way that it's handled is that it's really divided into like a typical two-stage approach where we focus the machine learning part on the predictive component, which is taking this observed data and trying to find as accurate as a possible model in order to predict the parameters we care about. And once this machine learning team, tool, whatever is designed, it's used in the follow-up stage where given particular observations using the predictions from the models are then fed into decision-making. And then there's another team of people working on, scalable optimization algorithms of trying to make the best decisions possible, taking the predictions as given, now as constants. And you can already see that there is a disconnect here, right? So although those two steps are inherently coupled, and the quality of the decisions that are going to come out at the end in terms of how they're going to play out in the real world depends both on our ability to optimize well as on our ability to actually get the right parameters, because garbage in, garbage out. If we get the wrong parameters, even if we find the optimal solution with respect to those parameters, we still have the wrong decisions deployed. So, for example, consider this setting where we have data like climate, time of day, the road network, etc., and historic data of delays on road segments. We can build a model, predictive model that tries to estimate travel times. And then with that model, we might feed it into a routing algorithm for a specific company that needs to compute shortest paths, for example, or other VRP style problems for their business, for example, to pick up and deliver certain goods to customers. Right, so this is from the point of view of what we want to do. This is really one continuous stream of our pipeline, of our system. However, in the two-stage training, what we'll do is we'll first take our historic data and really just try to fit a predictive model that compares the predicted delays to the actual delays and update our neural network, for example, model based on the accuracy with respect to that comparison. right? So we're going to try to make the predictions closer to the actual delay across all the data that we have. However, there's a challenge here because maximizing accuracy doesn't necessarily mean maximizing decision quality. We might have limited or noisy data, which means our model overall will not have high accuracy. Now we are making mistakes, and some of those errors in our predictions are basically spread across the possible space in an unguided way. We might be making prediction errors exactly at the road segments that are most critical and most likely to be used by the routes that our company cares about in the downstream decision task. So in this setting, when we have limited or noisy data, all models are wrong, but we really want to find the useful ones. So this two-stage training doesn't align with our end goal, which is deploy the best quality solutions that we can. So what can we do about this? What we want to do is to basically find a way to automatically shape the machine learning model's loss by incorporating the optimization problem into the training loop. Okay, so instead of having this accuracy of predictions versus observed delays in our example with the Google Maps, we really want to actually update the parameters of our neural network model based on the quality of the shortest paths that get generated based on our predictions, right? So we want to plug in the predicted delays into the optimization problem, get the shortest path, evaluate that shortest path with respect to the ground truth delays, and get that quality, decision quality loss as the feedback that we use in order to update predictive model parameters. And so this is what we refer to as decision-focused learning. The learning is focused on the decision loss, not on the accuracy loss. Okay, so so how can we address this? So we have our decision problem or optimization problem in, that we need to solve downstream, which will involve some kind of discrete decision variables, and will depend on some unknown parameters, which are the ones we're trying to estimate with our machine learning model. In our work, we focus on these parameters being the coefficients of the objective function. In the example that I gave, this is basically those travel times on each road segment. Okay, so the key idea of how to incorporate this full pipeline into an end-to-end system is to try to take derivatives of the decision objective, the decision quality we get at the end, with respect to the all the way back with respect to the machine learning model weights, right? And then train the model via gradient descent, because a lot of the powerful machine learning models that we have right now are really based on using that methodology. And in fact, a similar approach was proposed earlier than this work by Dante et al. In 2017, where they focused on a task-oriented problem, which was a continuous convex problem. Here we want to expand that technique specifically to the kind of combinatorial NP-hard problems that this whole tutorial has focused on. Can we do this? Okay, so the challenge is that we need to basically create this gradient computation from the decision quality of our decisions to our actual decisions that we took in our optimization algorithm, then take the derivative of these decisions with respect to the parameters that were used by the optimization, which were provided by our prediction component. And then obviously the standard thing, the predictions are a function of the weights in our neural network. So we want to basically go through this whole process all the way back during training. The challenge here is that the optimization problems we want to consider are discrete, right? And so the solution that we proposed in our 2019 AAAI paper was to try to find a way to relax these discrete problems to a continuous ones, and then find a way to differentiate through them to compute the gradients. And then at test time, be able to round these continuous relaxations to a discrete feasible solution. So basically, we'll take our binary or integer problem and relax all the discrete variables to continuous in order to get a convex Howe approximation. So how can we compute this critical component, which is differentiate the decisions, the values of our decision variables with respect to the parameters that we gave to our optimization algorithm, right? And so the key kind of technical aspect is to actually use the fact that the locally optimum continuous solution must satisfy KKT conditions. And in fact, these KKT conditions define a system of linear equations, which is differentiable. And that was the key part that was exploited also in the earlier paper by Donti et al. Okay, so for which classes of problems can we find a way to get this framework working, where we can take our combinatorial discrete problem and find a suitable continuous relaxation that will be able to exploit this idea? One broad family of problems can be encoded with linear programs. So linear programs model exactly many combinatorial problems like bipartite matching, shortest path, mean cut. They also can be used as a relaxation to more complex problems. So in the standard form, we basically have this linear objective, theta times x, and a set of linear inequalities ax less than or equal to b. So here, these theta are the parameters that are going to come from our predictive component, right? So these are the estimated upstream quantities. Unfortunately, even though it's continuous, the LP here still is hard to differentiate through, because we can basically switch unexpectedly from one corner of our feasibility polytope to another. So the solution here is to actually add a regularizer, which smooths things out, and then the derivative is now again well-defined. So this regularized version of the LP is actually provably differentiable and close enough to the original LP subject to this parameter gamma that we have. Similarly, for another broad class of problems, submodular maximization, which captures a lot of interesting real-world problems like influence maximization on graphs, etc. We have shown that we can find a suitable continuous relaxation based on the multilinear extension. And in the interest of time, I'm going to skip that result, but I'm going to show you experimental results with the submodular maximization in the context of decision-focused learning. The idea is the same. You relax the combinatorial problem to a continuous version where you can use the KKT conditions in order to derive gradients on the backward pass. So here are results on three types of problems: budget allocation, which is a submodular maximization problem; matching, which is an LP problem; and diverse recommendation, which is another submodular maximization problem. Matching is based on a data set of Cora, which is scientific papers with their citations, and diverse recommendation is based on a real-world data set from media lens, like movies, basically users rating movies. And so here we compare our decision-focused learning, which is NN1 decision, NN2 decision, to the two-stage approach where we first just train a machine learning model and then provide the estimates to our optimization algorithm. And we experiment with two different neural network architectures, NN1 and NN2. And so in these results, what we observe is that decision-focused learning consistently provides better quality solutions, 15 to 70% improvement in solution quality over the two-stage across all three domains. So just to connect this back a little bit to the earlier part of the tutorial, is here we are again in this distributional setting where our training examples, right, have these input features that go through the neural network that then go to define an optimization, combinatorial optimization problem. And so during training, we have a whole bunch of these both prediction and combinatorial instances that we train on. And then at test time, we have another set from the same distribution of unseen inputs and corresponding optimization problems to them. And so one thing I want to highlight is that typically the machine learning part of our model that is trained with the decision-focused learning is actually less accurate in terms of AUC or mean square error than the two-stage component. And that's to be expected. Obviously, in the two-stage approach, we are, in the first part, we are really trying to maximize that accuracy, right? In our case, we are not maximizing the accuracy, but we are making sure that we are not making mistakes where it matters most. So we are not making mistakes where it might confuse the downstream combinatorial decision-making. And so this basically integrating the combinatorics in the loop is providing important inductive bias to the predictions. So in a sense, you can think of this approach as really having incorporated the linear programming as a layer in the neural network training. And so can we go one step further beyond LP and submodular maximization? Well, before I go there, I guess I wanted to mention that in follow-up work, we use this decision-focused learning approach to a specific important application area, tuberculosis treatment, where we worked with an NGO called Everwell in India, where there was need to basically deploy health workers to visit TB patients in order to remind them to take their daily dose of medication, which is a very important regimen in order to achieve the benefits of taking the medication. And so the idea is, can we predict patients that are likely to miss their dose? And then based on those predictions, dispatch limited resources, limited number of health workers as effectively as possible, basically maximizing the impact of that intervention and having as many patients take their doses as possible. And so that was presented in a KDD 2019 paper, where again, with the decision focus approach, we achieved a 15% improvement in the decision quality of the proposed plans with respect to the standard two-stage approach, which would maximize first accuracy in terms of prediction, patient likelihood to not take their dose, and then apply the dispatching of health workers separately. So as I started saying earlier, can we go beyond this linear programming as a layer or submodular maximization as a layer to the more general families of combinatorial problems? In particular, as we have heard many times during this tutorial, mixed integer programming is a very broad family of models able to encode many hard NP-hard combinatorial problems from the real world. And so in this follow-up work at AAAI 2020, we basically extended the framework to have mixed integer programming as a layer in our end-to-end training of neural networks. And here we really very strongly leverage our previous result. We already know how to differentiate through an LP relaxation. And I guess trivially one could say, well, given a MIP, just take the LP relaxation of the MIP and just use the old result. The problem with that is that for many problems, the root LP, just relaxing the straightforward MIP to the LP, is too weak. It doesn't really capture a lot of the structure of the problem. Instead, we use the fact that if you use cutting planes algorithms to solve the MIP problem, what that does is that it iteratively adds additional linear constraints, cuts, to our problem that chop away parts of the solution space, of the discrete solution space that are non-optimal. And so at the end of this process, what we have is we have this expanded set of linear constraints such that when you actually solve the LP relaxation of this expanded problem, the optimum solution is integer feasible as well. So once we are finished with this problem, we actually have this big LP for which we can apply our previous framework, where we can just differentiate through the KKT conditions of that LP optimum solution. And so that's exactly what we do. During training at each pass, we are basically going through our neural network, predicting the objective coefficients of our downstream optimization, then running cutting plane approach, getting the big LP, and then differentiating back through that to update the parameters. At test time, you don't need to run cutting planes, which is a slower algorithm than, let's say, straightforward branch and bound in many applications. You just use your neural network predictive components to get those estimates of the objective coefficients, and then you have your objective optimization problem defined. You can at test time, at deployment time, plug that into your favorite solver like Groby or Cplex or Skip. Okay, so let's see how this works. So we evaluated this on 3 real-world data sets. Well, one, I guess, is semi-real-world. The first one, I am referring to the diverse bipartite matching, but the first real-world data set was portfolio optimization, where we are trying to predict the monthly rate of return. And then with these predictions, we want to optimize our portfolio of investments to maximize this return, subject to constraints like limiting risk, sector exposure, transactions, etc. And we used real data from SP500 from the USA and the DAX index from Germany for that setup. The second problem is diverse bipartite matching, where we want to predict the match success probability on an edge. And then we want to optimize the total number of real successful matches with respect to the ground truth, right? And again, we have matching constraints, like each node has to be matched at most one, but in addition, we added constraints like ensuring a minimum % of proposed matches to be a different or same type, etc. So these are some realistic side constraints that come up in real-world applications that make the bipartite matching not solvable by pure LP anymore. So for this, we use the Cora dataset of scientific papers and their citations, where the nodes are papers and the edges are citations between them. And finally, the energy production knapsack, where we are predicting energy prices. We want to optimize total revenue, and we have constraints on the number of time periods that we can use to generate the energy that's needed. And this is data from the ICON Energy Scheduling Challenge. So with these 3 data set, what we observed is that we can actually gain very big improvements by relying on decision-focused learning instead of the 2-stage. So here you can see, for example, for SP500, this 2-stage approach generates about 1.19 expected return versus our MIPAO approach generates 2.79. And as a second baseline, this root LP idea from our previous approach, which just relaxes the problem to an LP, you can see doesn't really work very well for almost any of the, for none of the domains. So big improvements, 2x on SP500, 8 times improvement on DAX, and smaller improvements on the other domains, but still 40% on the diverse bipartite matching and about 1.2% on the knapsack, energy knapsack problem. In addition, what we also evaluated in this setting is the idea of transfer learning. Can we learn on one distribution of inputs and then successfully apply to a similar but different distribution? So here what we did is we trained our portfolio optimization with data from only 30 of the assets. And then we tested on a separate set of 30 assets that were not seen during training, both from the USA, SP30B, and even in a different country on the basically 30 assets in the DAX data set. And what we observed is that, in fact, we can actually get this transfer of the prediction work pretty well with respect to both the models for, especially the models for the decision-focused learning, not so much the 2-stage models. And we also have generalization ability across larger sizes, so training on 30 assets, but then using it to solve optimization problems that involve 50, 100, 200, and 500 assets here. So in conclusion, I guess the decision-focused learning is highlighting the fact that there's no need to silo out machine learning versus the optimization task. When the data is scarce, we want the predictions to be accurate where it matters most for the decision making. And so we want to make sure that our loss is shaped in that way. And the best way to do that is to actually incorporate the decision in the training loop by marrying the predictive and the prescriptive tasks in an end-to-end system. I also want to highlight the fact that there is several related frameworks to the one I presented, such as the Predict and Optimize framework and its variant, as well as several recent papers on black box differentiation of combinatorial solvers. Elias, how am I doing on time?
I think maybe one more minute, because we have a couple questions for you and we're 10 minutes away from the total time. So
okay,
Andrea
so
conclude.
Then I think I'm going to stop here. I on
Okay.
purpose made my talk decomposable and not talk about the cluster net, which is a similar, I guess, just to give 1 minute overview, is this idea of being able to relax our combinatorial problem effectively, as what we've seen so far, sometimes fails due to scalability problems or due to just the structure of our problem. And another approach that we have considered is to actually come up with a surrogate that provides inductive bias that's still useful to solving the problem. And in particular, in our NeurIPS 2019 paper, we showed that for a lot of graph optimization problems, clustering can actually act as a very good surrogate. And we develop a differentiable k-means layer, which we call ClusterNet, which can be used again in this decision focus learning paradigm, where instead of just doing prediction, link prediction training, and then the graph optimization, we combine the two to doing the basically the graph input straight into the differentiable k-means, and show how that can be used for problems like modularity optimization, for community detection, and facility location in graphs. So I'm going to stop here.
Great. So one question is, you've mostly focused on predicting objective function coefficients. Are there any successful stories for predicting like constraint coefficients, or is that harder?
It is harder. It's harder to figure out how to create differentiable versions of that. So in particular, this framework with the KKT conditions that we have developed doesn't easily generalize to coefficients. There is recent work on using the differentiable black box approach in order to try to predict both coefficients and, objective coefficients and constrained coefficients. It was a paper at the NeurIPS 2020 workshop on learning, sorry, I'm losing my voice, on learning and combinatorial algorithms, LMCA. So in fact, I think I had that in my slide, but it's from the Max Planck Institute group that is doing this black box combinatorial solver. So they have some preliminary work on trying to attempt that. But I guess the short is, it's hard. It's unclear whether it's doable in real world settings.
So there is a nice paper by Michela Milano, Michele Lombardi, and Andrea Bartolini on empirical decision model learning, in which they actually learn also the coefficient of the constraints. So this is a reference that I put on the chat.
That's great.
Okay, and one last question quickly. Stefan asks, he's familiar with the Brandon Amos and Zico Coulter's paper, where they're able to solve a batch of QPs together to leverage a GPU parallelism. Is there a similar way to kind of parallelize in the MIP as a layer framework to kind of parallelize this computation efficiently?
The MIP as a layer, not necessarily, because you still need to do the cutting planes, but the LP as a layer, yes.
Okay.
Because it's straightforward. You already know all the coefficients. You just have to define the KKTs, right? But for the MIP, you still have that algorithmic part where you have to go through the process of generating the cutting planes, right? And so that has to be done. I mean, you can still parallelize it, but not. I don't think it's what you mean, the actual exploiting matrix algebra.
Matrix, yeah, exactly. Okay, thanks Bistra, and thanks everybody for sticking around. So we'll conclude now with Andrea Lodi. Andrea?
Yes, let me share my screen.
Yes, we see it.
Yes, and do you also see me?
Yes.
Okay, good.
All good.
Good. So it's my pleasure. My name is Andrea Lodi. I'm a professor at Polytechnique in Montreal, and I'm somehow one of the let's say component of this team. So I'm very happy to be the one that is actually concluding this very nice overview given by all my colleagues. And what I will talk about today is some generally concluding remarks, and I'm ending with a question about the bright future of what we are actually somehow presented over the entire tutorial. And I would like to remind you a few things before doing that. So I'm finishing with questions. So what we have tried to convince you is that integer discrete optimization, combinatorial optimization is a very, let's say, interesting area in which there are a lot of applications that will be solved better through, for example, the integration with machine learning could actually eventually very much help in improving our lives in energy, transportation, and telecommunication and many other areas. We also try to convince you that there are been given the impression in many parts of this tutorial that the repeatedly solving the same problem multiple times is a very important component of it, especially because of mixed integer linear programming solvers were not designed originally for this. So they're not exploiting the fact of using essentially just small variations of the same data for solving iteratively in applications, the same application multiple times. So what we are also covered is three different paradigms that we have seen in which the integration of essentially discrete optimization and machine learning techniques has been already exploited and explored recently in the literature, and especially one is the so-called what I like to call end-to-end learning. So given the problem definition, the machine learning algorithm is taking place in order to define the feasible solution and somehow a heuristic solution for the problem. We also discussed about the learning, what's going on? The learning properties. So this is the situation in which instead the machine learning is actually used for somehow simplifying the problem at the beginning, for example, deciding about some characteristic of the algorithm that you want to use, or the linearization of the objective function, or various things like this. And another alternative is learning repeated decisions. In this particular case, we are talking, this has been extensively discussed by Maxime and also Giulia and Laurent during the talk about, for example, learning the branching decisions, which are a fundamental ingredient, a component of branch and bound methods. So I think that this has been touched and mentioned multiple times during the entire presentation. There are a bunch of challenges that are still really very much into the game in order to understand if this is going to be like effective, extremely effective in the future. The future is going to be bright or not. And one of the most important one that I think I care about is the one of the metrics. So the classical metrics minimizing the loss function in machine learning do not generally or necessarily align with the combinatorial optimization metrics, which is the most common one is shortest computing time. So Laurent discussed this very deeply, also Giulia at the same time. So this is actually one of the most important questions around this, and we have to face it from the theoretical and methodological standpoint. What instances do we want to generalize to? Again, has been discussed very much into the tutorial. So we want really to understand how to build something that goes not generalizes only not on the size. So we are learning on small and then applying it on larger problems, but also try to generalize to instances outside of the distribution. So transfer learning, fine tuning, and meta learning are things that definitely are on the map in order to do this better and better. And for example, for the specific case of learning to branch, this first step has been given recently in a few papers. So what the distribution of the instances which are interesting, of course, this is another question that we care about, and essentially this is the idea of looking at applications, even if, again, Laurent has talked about the data, so the difficulty of maybe sharing or having enough data for real-world applications, which will be enough for machine learning techniques in order to run extensively and finding solutions. So the challenges are not only there. So we have the question is which one of the deep learning or imitation learning and also reinforcement learning techniques or models are going to be the most important ones. We've seen graphical neural networks have been very useful in many type of application in which capturing the structure of the problem, but the representation itself of the data is, as we've seen, difficult. So we need architectures that are actually collecting this information and making them use of them in the best possible way. Scaling is, of course, super important in the computation. We've seen a recent attempt to actually use neural networks a little bit less in order to facilitate the integration of machine learning techniques, which have been used with essentially GPU very much in the context of branching, in which generally speaking combinatorial optimization methods will work on CPU only. Generalization and learning are also scaling issues which are important, as well as how to generate the data, which have been extensively discussed by Laurent. And finally, an important point of view is this has been covering combinatorial optimization, so discrete optimization, or mostly mixed integer linear optimization. And now the question is, what can we do for mixed integer non-linear optimization? So problems which are even more complex, or situations in which more than one objective function has to come into the play. So in summary, I like to say that we start to have a mild, but I mean solid evidence that the integration between machine learning and combinatorial optimization could be effective, and the needs in our view are pretty much. I mean, there are many let's say needs that are actually bringing the idea of using machine learning together with combinatorial optimization, especially for applications, and there's certainly some of them are dealing with big and uncertain data, and there is a recent amount of work dealing with producing, I mean, looking at stochastic optimization, so problems in which the data itself is stochastic, as it's not deterministic. And of course, one part that has been covered is also looking at using modern statistics either to look at mathematical characterizations which are hard, so situations in which it takes, I mean, we don't really fully understand what is the best strategy for solving from the mathematical standpoint for solving the problem, so or for dealing with a particular characteristic. For example, on branching, a strong branching approach is a good heuristic, but we don't actually know what is the best branching method that we would like to use for the problem. And or on the other hand, when it is what the mathematical characterization that we have is too slow to actually be usable especially at large. And I'm finishing again with pointing out that repeatedly solve the same instance or instances with in which the data has changed very little is something that I mean, the history of mixed integer linear programming has not really worked very much, and I think this is one of the most pressing among the challenges and the questions that we would like to take in the next years. So I'm done, and I would like on behalf of the rest of the tutorial speakers, thank you for your attentions, for all the questions, and of course we are happy all together to take even more questions if you have them, or later on by email and in every other means that you would like to.
Great. Thanks, Andrea. I just linked the website for the tutorial, which has the slides already, and we'll have the video. And it's also linked on the AAAI webpage if you look at the top on the tutorial website. And they should add the video recording of this once we upload it there. Yeah, if the presenters could maybe put their video back on. And if there are questions, then I think some of us are still around and we're happy to take them.